Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. I want to thank you for taking the time to join us here today. I want to talk to you about the next of our function families, or types of functions that we tend to encounter in an Algebra 1 classroom. We've already talked about several of those, and for the sake of brevity, I'm not going to run through those again, but certainly the lessons immediately prior to this one are ones you can look at to discover those. Our goal is to look at all the functions one at a time, or an example of each of those, and then go back and talk about things they have in common, things that they have different, and how we can begin to anticipate what our functions are going to look like before we begin to graph them. Notice that this is x to the third power. When the highest degree exponent is a 3, you call it a cubic function. A cubic function, and all cubic functions are going to form pretty much the same type of graph. Just like before, I am going to create values for my domain. I'm going to put them into my function. My function is going to spit out a range that I can then use as a coordinate. I am going to begin moving through the tables a lot faster. Now that we've done this a couple times, you should be able to stick in values and solve on your own. And then I want to spend my time looking at the function and talking about some of the features that it happens to have. So here we go. If I stick in a 0 into my function, 0 cubed minus 2 is 0 negative 2, which is here. If I stick a 1 into my function, 1 cubed minus 2, that's 1 minus 2 is negative 1. If I stick a 2 into my function, I get 2 cubed minus 2, which is 8 minus 2, which is 6, which is here. If I put in a 3, I get 3 cubed is 27 minus 2, which is 25. That grew really fast, didn't it? Doesn't actually fit on the coordinate plane I've drawn, but just know that it would be somewhere over here, 3, and then way up here someplace. That actually is very useful to me because that tells me that when I leave the space that's available to me on my graph, I have to leave it before I reach 3. Since I'm out of room on the right, let's go to the left. Negative 1 cubed minus 2. That's negative 1 minus 2, or negative 3. If I stick in a negative 2, I get negative 2 cubed, which is negative 8 minus 2, which is negative 10. If I stick in a negative 3, I get negative 3, which is 27 minus, or negative 27 minus 2, which is negative 29. Negative 29. So negative 3, negative 29. And I'm out of room again. Negative 1, negative 3 is about here. Negative 2, negative 10 is here. And I kind of am out of room. You can actually hear the bell from my own class getting ready to start here in just a moment. As you look at this graph, can you see the pattern that's occurring? Notice that we said it's going out here. It's very, very steep, but then it starts to shallow up just a little bit. What I want us to pay special attention to is this space right in between here, because it looks like that is linear, but it's not linear. If I plug in a 1/2 to the third, that's actually 1/8 minus 2, which is negative 1 7/8, which is clear down here. If I do a negative 1/2, I get negative 1/8 minus 2, which is negative 2 1/8, which is here. You see, this graph doesn't go straight across, so it actually curves down, almost becomes straight, and then starts curving again. So you end up with something kind of like that. It's important, if you ever have a spot in your graph that's unclear to you, just pick a point that lies in that spot or a domain that lies in that spot, insert it in and see what happens. It'll usually clear it up. All your cubic functions are going to have the same basic shape. They're going to start up on one side, come down, flatten out, and come down the other side. Now, the whole thing could be moved to the right. The whole thing could be moved to the left, up, down. I could put this anywhere on the coordinate plane. I could even flip it upside down. I could stretch it wide. I could make it tall and skinny. But they will all have this same basic shape. A couple things I want to point out to you. If I'm just looking at how this goes to the right, it does go to the right forever. It's getting pretty steep, but it does keep going. It does go to the left forever, so my domain is all values of x as long as x is a real number. Remember, that means any number on the number line. If I look at how this goes up and down, notice that it goes up forever. It also goes down forever. So we would say that this function has a range of all real numbers as well. This says any value of y or f of x will work as long as that value is a real number. This is function notation. We talked about it in our earlier videos. A couple features I want you to recognize. First of all, this is your y-intercept because that's where you cross the y-axis. It is the point 0, -2. That also happens to be your vertex because at that point your graph changes its behavior. You can see it's coming shallow, or it's coming very steep and getting shallower, 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 and then it gets shallower and steep again, or the other direction, steeper, 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 steeper. The slope is changing and slowing down. It reverses and goes the other direction. Very important. I can't actually see what the x-intercept is because it is a decimal. What I do know is that it will be something comma 0 because when we touch the x-axis it's always over a certain amount and up 0, which means I can compute it. I take my function and I put a 0 in for y or f of x. I use the property of equality to get rid of 2, and then I use a cube root to get rid of x cubed. Now most of us are not going to do cube roots on our own. In fact, I could probably make an argument that you could leave this as the cube root of 2 comma 0, but I know that makes a lot of you uncomfortable. If you have a graphing calculator, you actually do have a cubic root function on your graphing calculator. If you go into the math menu, and press that, you can see you have lots of different options here. One of those, choice 4, is the cube root. So I can take that, type in, what did we say, cube root of 2. I could type in a 2 and close my parentheses, and it will actually give me an estimate of that decimal value, 1.26 comma 0. So your x-intercept would be 1.26-ish comma 0. Other features of this particular function would be that it does not have a line of symmetry because you cannot reflect one side to the other, but it does have rotational symmetry. It does have rotational symmetry around the point 0, -2. So if I were to hold this spot down and spin this like a fan, this top curve would come down and match the bottom curve and vice versa, so that we can begin to see that it matches and spins. I am going to cut this short. You can hear that my students are coming in now. Thank you so much for joining us. If you found this helpful, make sure you leave a comment in the comment section. Make sure you like and subscribe so that you can follow along with us as we learn Algebra 1. This is, I believe, the 4th of our 7 different function families we're going to concern ourselves with. Please come back and join us for the others. Thank you very much. Have a great day.